up, and your character has to dust it off like it was his idea. And it's like, no, sorry, I'm not moving.
Sorry, forgive me.
Oh, I mean, I didn't notice if you did.
Sure. Speaking of the word diegetic, the best Disney song is All Is Found, because it exists in the world of Frozen. It's not just a song that people sing. It's like, it is a song that exists to characters as a song, rather than like, yeah, that one time that Elsa went outside and started yelling about, you know, like, it's not I'm gonna get eaten. Oh, okay. It is a song that exists, and I think that that's very cool. Like, the world has music beyond just what like people are singing. There are also songs there. Does that make sense?
Yeah, no, it's like, although I think the diegesis of all of the songs in Frozen 2 is a little bit confusing. Because every song Elsa sings is because she's hearing like a magical siren call.
True.
So we can assume that her singing back to it, which she does, and causes it to respond, must therefore be happening in the universe.
Yeah.
It's so that's confusing. I think the only number that we can guarantee is non-diegetic is Lost in the Woods, which is also the objective best number.
Definitely not anything that happens in the realm of reality. Because poor Kristoff is clearly losing his mind.
The reindeer backup singers kind of take it out of the realm of reality. But
like, I don't know if your boy, like, or I guess our boy, because we are viewers and he's a character, like found some shrooms in their woods, but he's not in his right mind.
Well, I mean, you know, sometimes your girlfriend leaves on a magical adventure because her sister left on an even more dangerous magical adventure, and you just gotta sing your feelings out.
Oh my gosh, look at this. Review.
I think it was just payback for the fact that they cast, you know, noted Broadway singer Jonathan Groff in the first movie, and the only song they gave him was "Reindeers Are Better Than People."
Oh,
so for the second one, they were like, "All right, I gotta sing a hair metal ballad in the style of Queen." He was like, "Only if I get to do all the parts."
Petting the fox, it's so good. The fox smiles and bounces, gets so excited. Ah, that's great. Let's see what's going on. Thing. Ah, yes, we're going over to get Heavenly Strike. All right, coming up on 2 hours here. Not bad. Yep. Not bad at all. Probably right after we finish this little side quest, because
sounds good.
I really need to get some light. Well, if we feel like we're doing good, then maybe we keep going. I don't know.
Maybe.
We're also going to stream this on Thursday, so we're not in any rush.
Yeah, we've got plenty of game to go.
Yeah.
To a certain extent, I think this is like the chill one because not much plot is really happening, and we're both like, "Oh yeah, game stuff." But I think once like the twists start flying, it'll be like, "Oh, okay, oh, beautiful."
Okay. Do you really? Do you really? Hello, everyone. About the homework and midterm, there is a homework due on Monday. So, midterm one, 2 weeks down the line. 2 weeks after the homework 2 is due, we have the midterm. We were discussing motion in one dimension, and today we want to concentrate on a very specific case, and that is about uniform acceleration. So let me quickly review or mention whatever we did last time. We were discussing motion in one dimension. There are few quantities involved. There is time, which is t, right? So t evolves in time. Often we have an initial and final situation, and that will be what will happen today. But in general, we just have a time t. It could start from 0 or any other point in time. That is position, and that's x. If we are in one dimension, we don't need to talk about a vector. Otherwise, there are three components of this position vector, which are the 3 coordinates in 3-dimensional space. But we are in one dimension. It's all happening in one line. So this position is simply a function of time, t. That's it. And usually that is the goal, right? When we say we are wanting to predict something, it's all about finding the position of an object at a future time in particular, but for that matter, at any time. For example, a spacecraft leaving from Earth today and landing on Mars 6 months down the line, that's position as a function of time in the future. So that's a remarkable even though we're reasonably good at it these days, but still we should appreciate that. Often, sometimes, which is what we will do today, it is easier to deal with two specific times, initial and final. At that time, we'll talk about change in position or displacement. We define velocity. That's v as a function of time, which is basically the derivative of the position with respect to time. So in general, it's a function of time. And acceleration. It is also a function of time, which is derivative of the velocity with respect to time. It is a change in velocity. How much are we changing the velocity? In terms of position, it's the second derivative of position with respect to time. It's good to have an intuitive feel for it. Velocity, typically, we all know any kind of motion that we see is what velocity is. Acceleration, sometimes it could be a little harder to imagine or intuitively understand what acceleration is, even though all of us have a very good sense of acceleration in an internal, in our mind, we know what acceleration is. But if we want to define or have an intuitive feel in terms of words, if your car is moving, if you're in a vehicle and if it is moving, and if you're steadily sitting on it, that means most probably you're not accelerating. But if you have a tendency to move forward or backward, right? Sometimes when you press on the brakes, your tendency is to move forward, right? That's acceleration, whatever you feel at that time. Or the easiest, best way of saying it is that if you have ever gone on a roller coaster ride, the sense of fear that you feel in a roller coaster ride is because of the acceleration. Our body is very sensitive to acceleration, and it thinks that you're falling. Like our body, the moment it senses acceleration, it gets this feeling that you're falling, and that's the fear that you get from roller coaster. Sometimes it also gets exciting if you overcome the fear for many of us or for many people, it could be also entertaining, and that's the idea. And we'll talk about those quantities a little more specifically later on. Now, I want to start with some notations a little bit. So, as I said, x as a function of time, that's what we are talking about. Sometimes we deal with x initial, so we will use the notation x subscript I, so that's initial. I stands for initial. That means position at time t initial. That's what we will use. So that's a notation if you want. X final similarly will be x at time t final. Often t final itself is sometimes t initial will be 0 and t final will be t. And we will do this pretty freely. Sometimes we'll talk about final time, sometimes we will talk about t itself to be the final time, and it could be moving along in that sense. Similarly, velocity initial is velocity at time t initial, and velocity final would be velocity at t final. Same thing stands for acceleration. Whenever we write acceleration initial, acceleration final, it means acceleration at the specific time. One more quantity which we defined already in the last class is that a change in time will be t final minus t initial, and if I use t, then it is t minus t initial. Delta x similarly is x final minus x initial. And So that's your notations. It's very clear, initial and final. In a path that you have, typically you are interested in a particular point in the futuristic time. That's your final time, and initial is most probably your present, right, today. But it doesn't have to be today or tomorrow. It could be even in the past, right? It doesn't really matter. We will also sometimes use V naught to represent initial time, but more specifically, it also means when it is constant, right? But we will also sometimes use it when it is initial. This will be constant, right? If V initial is a constant, then we will represent it with that. A naught would be constant acceleration, constant velocity. It doesn't have to be the case. If velocity is changing with time, it is probably not a good idea to use V naught, but that will be a notation. And since the initial velocity is a constant, it doesn't even depend on time. Sometimes we will also mean this to V initial or V at time t equal to 0. If it is constant, then it stays the same all through. That's one way of looking at it. This is constant acceleration. If acceleration is not constant, you will say this is acceleration at initial time or at time t equal to 0. If it is a constant, it remains the same all through. So that's roughly the notation we will need. So let's talk about a specific case. We will talk about two specific situations. One is motion, or let's say uniform velocity. As uniform means it stays the same. Velocity remains the same. So this means V remains same, remains constant. That means it doesn't change with time in particular. Immediately we can say, what about acceleration? Right? Acceleration is rate of change of velocity with time, derivative of velocity with time. But we just now said that we are considering the simple scenario where V remains constant. That means acceleration is 0. Right? So it does not accelerate. So that's a conclusion we make. So acceleration is equal to 0. Of course, it's constant if it is 0. It remains 0 all throughout. So what else can we say? It also remains constant. So let's say velocity is V naught, let's say. So that's velocity is dx by dt. And we are saying that this is a constant. So let's say this is V naught. Right? In general, it is a velocity as a function of time. This is a constant. That means with the subscript, we clarify that that's a constant. We can now integrate this equation for the position. Right? So I'm going to integrate. So notice this was a ratio, right? Even though we always learn that this is an operator, d by dt operates on the function x, but it is in principle a ratio in the limit delta t tends to 0. This is delta x part over delta t. So split that ratio, release the limit for a moment, and take it to the right hand side. So that allows us to do integration. So that's V naught times dt. So then integrate both sides. So we are integrating this, but this is not a function of time. This is a constant. Right? So if it is not a function of time, it can come out of the integral. Before that, I can also give some initial and final limits to this. We would like to go from, this is an integral over time. So I go from initial time to final time. Two distinct points in time. And in that time, the position changes from initial position to final position. But both these integrals are trivial, right? Remember your integral dx is simply x, correct? If that is a to b, then you just evaluate it at a to b, so that's b minus a. Am I within the boat? Yes. Okay. So that's b minus a. If it is timed integral over time, it is t integrated from initial to final. So that's the simplest integral you can do. On the right hand side, v0 is a constant, so it can come out of the integral, and then that's a straightforward integral again. So what we get is this is equal to x final minus x initial is equal to v naught times t final minus t initial. But that in our notation is nothing but delta x. Correct. So that's delta x is equal to v naught. Am I within the board space? Yes. Times delta t. And if I were to move this, so I can also write this as change in position over change in time is just the velocity, right? That's a standard definition of velocity itself, but this is slightly more than your standard velocity, because this is any two positions. Typically, we define velocity as rate of change that we have to take the limit delta t tends to 0. But if we are going with uniform velocity, we don't have to worry about calculus. It is just a ratio of any two or ratio of any displacement between any two times and divided by the time difference itself. So as a summary, so what are the important equations when we are talking about uniform velocity? One of the simplest motions you can think of course, it means v is equal to v naught. So it remains a constant. So this is a constant. And the rate of change in position or the displacement over the difference in time, not necessarily in the limit delta t tends to 0, always that's equal to v naught, and importantly, acceleration is 0. And the plots are nice. If you plot x as a function of time, it's a straight line. It doesn't have to start from origin, so it's a straight line. And if you were to plot velocity as a function of time, this is constant, right? So it's v naught. Again, one of the simplest motions we can think of. Now we want to do the next case when it is moving with uniform acceleration. Again, I don't want to give you the impression that these are the only two possibilities. These are one of the two simplest scenarios. And the interesting part of these two cases is that we can just deal with algebra. We don't even have to use calculus. We can actually talk in terms of differences in time and not really worry about instantaneous velocity and instantaneous time. But always we mean, whenever we say initial velocity and final velocity, we do mean instantaneous velocities at those instants. But to process things, we don't need to strictly use calculus. We can pretty much use algebra for these problems. And they are very powerful tools. Many of the problems that we will see can be done very interesting. Classic problems can be worked out in this manner. So we want to spend some time on it. So let's do uniform acceleration now. We'll first derive our equation, relevant equations, but we will see that when we are working on problems, that especially your homework problems, algebra will be sufficient, even though I will derive them using calculus. Eventually, once we get the equations, we will be able to work with simple algebra, algebraic quantities. But all this is true only for uniform acceleration in real life. It's a good approximation, but most of the problems are not. The classic problem is, of course, throwing a stone up in the air. That is uniform acceleration. So most of the problems we'll deal with will involve throwing a stone up in the air. Okay, so uniform acceleration, what does it mean? So A is a constant. So let me write A as a function of time. So A as a function of time is a constant. Let me call that A naught. Constant. It doesn't change with time. Acceleration is rate of change of velocity. So that's A naught. So that's a constant. Again, use our trick of integrating. So that's dv is equal to A naught dt. So split the derivative into as really the ratio what it was originally, but release the limits and then think of integral as a limit, in the sense that integral is basically adding a lot of infinite number of infinitely small quantities. That's what an integral is about. We are adding quantities. Again, we integrate on both sides. A naught can come out of the integral. We do the integral from t initial to t final. In that same situation, the velocity changes from v initial to v final. So we get, again, the integration is straightforward. There is no velocity here, so it's simply v evaluated at v final and v initial. So that's v final minus v initial. A naught comes out of the integral. Remaining integral is straightforward, just linear. So it is A naught times t final minus t initial. So that's an equation we learn. So this is usually, you will come across it more commonly as v final is equal to v initial plus A naught times delta t. Again, only if this is uniform acceleration does this equation work. If it is not uniform acceleration, what changes? This quantity A naught does not come out of this integral. This is a function of time now. We need to know what exactly is that function, and that integral need not give you this simple scenario here. So that's going to be one of our equations of motion. We'll call it kinematic equations of motion. In principle, derivative of velocity with time is the most general scenario, but under uniform acceleration, there is a simpler algebraic form to that, which doesn't require calculus, and extremely powerful tool, as we are going to see. We will be able to work on a lot of problems based on that. Okay, so that's velocity. Go back to, now let's do some trick here, just so that we can do one more integral. So I'm going to change my notations a little. All the final velocities I'm going to replace. So all the t final I'm going to replace with t, just so that I can integrate, right? So I want the t in my hand. So that's velocity as a function of time is equal to v initial. I will keep it as it is. Plus A naught times t minus t initial. Just replaced all the final velocities with, or final quantities with a variable t in it. But dv velocity is nothing but dx by dt. And I can use the same trick now. I do the dt on the right hand side. So that's dx is equal to v initial times dt. Since there are two terms, I have to multiply on both terms, plus A initial, A naught times t minus t initial times dt. Again, integrate all three terms now. Time goes from t initial to t final. position goes from x initial to x final. The same idea as earlier, except now since we are in uniform acceleration, so there are two terms and we have to do both quantities. This is, we came across earlier also. This is nothing but x final minus, oh, this is x final, right? X final minus x initial. So that's just a change in position or the displacement, which we have been using delta x to represent that. V initial does not depend on time, right? V initial is the initial velocity. It remains the same. There is no time dependence in it. So that this integral is also straightforward. So it's V initial, and that's T final minus T initial. I'll write that as delta T. And the next term now, so that's dt T minus T initial. This T will lead to T squared over 2. This will lead to a T, and when you substitute your T final minus T initial, you can show that this integral is equal to half A naught delta T squared. So just to give you some hints here, so what I have to do this integral is first substitute T prime is equal to T minus T initial. So that's a new time, remember your substitution, then your integral will become A naught, this is T prime. When you make this substitution, this is not changing in time, so dt prime is just T prime itself. So that's dt is substituted as T prime. And when you do this, your limits change from 0 now, because at t equal to t initial, that's 0. And on the top, this is t final minus t initial. That's a straightforward integral, t integrated with t prime. So remember, right here, yes. So if I were to do x dx, that's x squared over 2 as an indefinite integral. And then if there is a to b, I'd evaluate it at a to b. So here we have t dt. So instead of x, we have time, or in fact t prime. So that's equal to a naught. So that's a half a naught t prime squared, and which you are evaluated at 0 and t final minus t initial. And that's what gives you this term in here. So that's your new equation, right? Position displacement is equal to initial velocity times change in time plus a contribution from acceleration. In fact, if you notice, if acceleration was 0, which is our first case of uniform velocity, that gives you this expression. So in general, this is the contribution coming from uniform velocity, but if it was accelerating, there is a new term in there. And that's our new equation for uniform acceleration. So we have two equations now. One is for between velocities, initial velocity and final velocity, and this is the displacement, final position and initial position. So let's process this more. We want to collect some equations before we can work on problems. And once we collect these equations, even though these derivations require integrations and differentiations, we will deal with algebra after that. It will be a lot more easier and less overwhelming for those who are really beginning the calculus. But in principle, everything can be done using calculus. Okay, so what we have is we have two equations now. V final is equal to V initial plus A naught delta t. So that's your first equation. Let me process this before I do that. Let me write the second equation. I'm going to leave some space. I want to fill in one more equation there. The second equation we got is delta x is V initial delta t plus half A naught delta t squared. We have two definitions for velocity and position, and we got two equations. And that's all we can get. We cannot get any more equations, but we can always manipulate these equations. Given two equations, you can rewrite it in different forms. So the first thing we'll do is we want to add or subtract these equations. So before that, let me change this equation, rewrite this equation a little bit. So I'm going to multiply by delta t all over. Whatever I do on one term, I have to do on every term, right? I multiply by delta t and then divide by 2 so that the third term looks exactly like this. So I'm going to divide by 2 in each term and multiply by time. Divide by 2 and multiply by time. And the third term is exactly the same as what is in the next equation. And the reason I do that, that allows me to subtract, and there's a simplicity in it. So I'm going to subtract these two equations. When I subtract them, these two just cancel out, but rest of them contribute. That's delta t minus delta x is equal to, these two are pretty much the same, so it's half minus 1, that's minus half the initial delta t. Put it on the, take this onto, or how do I do this? This is onto the left and delta x to the right, and then switch it all together. And this has a form. If you rewrite this, delta x over delta t is equal to v final plus v initial over 2. That's interesting in the sense, if you were to look at this right-hand side, remember if you are going with uniform velocity, this ratio of displacement over time, even without the limit delta t tends to 0, that was your constant velocity. But now we are not going with constant velocity. Velocity is actually linearly changing, but notice linearly changing because we are going with uniform acceleration. It seems like the velocity that you could have defined in uniform velocity is nothing but instead do an average of the final and initial, which is, even though very intuitive, it shouldn't be confused with average velocity. It is just a coincidence that initial plus final averaged out gives you your average velocity again. So let's look at that more closely. So that's your third equation if you want. That's your third equation. We'll collect them. We're going to collect 5 equations. But before we go into the fourth and fifth equation, let me point out a few things about this. There shouldn't be any confusion about whether this is average velocity or not. And in the last class, I even mentioned that I won't talk about average velocity very much, but this is a conceptual point. So let me for a moment define what is average velocity and calculate that for uniform acceleration. And I'll show that that turns out to be exactly this. But that doesn't mean that it's always the case in every case, every scenario. Only for uniform acceleration, it works out. So let's quickly do that. So let's change the mode. So let's do uniform, no, what was I doing? Average velocity, right? So it's average velocity. If we average the way we understand it is, so let's say this is your time, and that's your velocity. And I don't want to be in uniform acceleration for a moment. If it is uniform acceleration, it will be linear, it will constant, it's just a straight line, right? So let me say this is uniform acceleration. So A is equal to a constant. But that's not the scenario I want to work on. This could be general. So this is non-uniform A, general, very general. In general, the velocity could be any function of time. In that case, how do I define average velocity? Average is, average of a quantity is you add up all the quantities divided by by the number of quantities that you have. So the velocity keeps changing arbitrarily. So I have to pick each of these points. In fact, at every instant that is a velocity, I have to add up all those quantities and then divide it by time. Right? So add up all those, that's an integral, right? So add up all these quantities, which is, since there are so many of them, so I'm going to add up all the way from t initial to t final, and that's velocity as a function of time. And adding is nothing but integral, right? The key point of integration is that it is adding, but it is adding infinite quantities, in the sense at every instant that is a point. So integral is adding infinite quantities, which are all infinitely small, because if you add infinite quantities, most probably you'll get an infinity. But if you're adding infinitely small, infinite quantities, so infinite of them, but each one is pretty much tiny, so then you have a chance of getting something finite, and that's what integral is about. So that's adding all quantities. That's a numerator of the average, but I have to divide it out by the number of quantities, which is measured in terms of difference in time itself. Right? So that's t final minus t initial. That's a general expression for average velocity. So that's very general. We would like to do this for uniform acceleration. And in that case, this is nothing but delta t, even otherwise, that's delta t, t initial to t final. The velocity as a function of time for uniform acceleration is v initial plus a naught delta t. And let me write that as t minus t initial. Should be t final, but I'm replacing it with t so that I can integrate over t. And dt. I replace the acceleration with that. This is true only for uniform acceleration. So whatever conclusion we make is true only for uniform acceleration, which is a conceptual understanding. We shouldn't, even though we do a lot of uniform acceleration problems, it doesn't mean that all the results generalize to general expression. Do this integral. This is 1 over delta t. This integral can be done. We just now did it on the right hand side. So that's v initial times delta t plus in half a naught delta t squared. That's the integral if you do, which we did a few minutes ago. One of the delta t's cancel out. That's v initial plus half. So that's plus half a naught times delta t. Let's rewrite this a little bit. That's equal to, I'm going to write this as 2 times v initial. So I add a v initial. But that's not correct, so I have to divide it by 2 then, right? So that's divided by 2. So that's the same as v initial itself. That allows me to factor out the 2 here, plus a naught delta t. And that gives me the feature that this is nothing but v final, right? So that gives you the fact that this is v initial plus v final over 2, which is what is the result we got. This is the average velocity. So this is equal to delta x over delta t, displacement over time. Turns out to be the average velocity, but only for uniform acceleration. So this is v average. Best is not to get confused with v average too much. So it is correct concept, but it is only for uniform acceleration. So be aware of it. Okay, so once we have these equations, let's, I said we will get 5 equations. Let's get all the 5 equations, and let's quickly do a problem also related to that. All right, get the strategy also to work on problems. Okay. In the pursuit of collecting 5 equations, we have got 3 of them. We have now got delta x over delta t is equal to V final plus V initial, right? That's one of the equations we got. There was a divide by 2, which I'm going to write on the left-hand side. Manipulated it, wrote it on the left-hand side. There was an initial, one of the first equations that we got was acceleration times delta t. Again, rewriting it in different ways. I am writing it on the left-hand side now, and this is V final minus V initial. Good. I have two equations now. Again, add, right? Why not? You can add these two equations, and we see that 2 times delta x over delta t plus a naught delta t. The V initial cancels out, and I have 2 times V final. I want to rewrite this in a slightly different form. What I'm going to do is in each term, I'll multiply by the change in time and divide out by 2. So that's delta x. And I will also move the acceleration term to the right hand side. So I'm dividing by 2 and multiplying by delta t. That's that term. And the acceleration term becomes a negative now, half of a naught times delta t squared. This looks very similar to one of the equations that we derived earlier, but it's not the same. There is a negative sign. And this is V final. Earlier we had a V initial. If you look into your notes, I can try it on the board, but it's not in the visible screen. Right? So that's a new equation you have got. If you had subtracted these two equations instead of adding, you will get back your original equation. Okay? So you would get back your delta x V initial, because now V initial will add up, and this will be half AT squared. That's good. So now we have got 4 equations, one more, and that is got by, instead of adding, I've added, I get this. If I subtract, I get the equation previously derived, which was done using by integration. But so addition, subtraction gone. The third operation is multiplication, right? So let's multiply these two equations. And when I multiply these two, the change in time is in the denominator in the first, change in time is in the numerator in the second. So they cancel out. And what I get is 2 times a naught times delta x. That's my left-hand side. And when I multiply these two equations, I get V final plus V initial multiplied by V final minus V initial. If you recall your algebra, this is of the form A plus B, A minus B. That's A squared minus B squared. And that gives you your 5th equation, and which can be written as 2 times A naught delta x is equal to V final squared minus V initial squared. So that's your 5th equation. So why all this collection of equations? Let's give a strategy of what kind of problems we are going to discuss now. So let's. Okay, so again, remember we're talking about uniform acceleration. And the simplicity is that, of course, there is this interest because we are talking about throwing a stone up in the air, and throwing stone up in the air looks like a simple act, but if you master this, it becomes very quickly a weapon, in the sense when you throw a very huge object at a very huge distance, that becomes a projectile or a missile, and it has been used in warfare for long. So this was used for horrific, but that's one of the applications of this. And if you actually do it a little farther from there, then it becomes a spacecraft, and then it becomes an exploration. So assuming that it's peaceful, so that's kind of nice too. Anyway, so what are the quantities? And I said this is all going to be algebraic, right? We can forget about the calculus for a moment, and we realize that there are 5 variables involved. That is change in time, that's initial time and final time, but we can set one of them to 0, so that's change in time. That is change in position. Then there is initial velocity, there is final velocity, and that is, since it's uniform acceleration, it is a naught. So that's the 5 variables, but we have only 2 equations. Why 2 equations? Because there is a definition of velocity and definition of acceleration. That's only 2 equations, but we manipulated it and got 5 equations out of it. But we should remember that there is only 2 equations. That means I can solve for 2 of them. Like that's a prediction now. Give me 3 quantities, I will tell you what is the next 2, what is the rest of the 2 out of 5. That's the prediction part we are talking about. Out of these 5 variables, given in a problem, you have to look for 3 variables always. Okay. So what's the strategy then? First, collect all the equations, right? So our equations were delta x over delta t. That was v final plus v initial over 2. That was v final is equal to v initial plus a naught times delta t. And then we have delta x is equal to v initial delta t plus half a naught delta t squared. That's the 3rd equation. 4th equation is, notice the difference. This was initial velocity, this is final velocity, a slight difference, minus half a naught delta t squared. And lastly, we have 2 a naught delta x is equal to v final squared minus v initial squared. Before I proceed further, let me define what is called a missing variable. So this is going to be a missing variable. It is not the quantity that is the unknown variable. So I will differentiate between an unknown variable, which is what we are looking for in a problem, and this is a missing variable. This is what we don't talk about in a problem, if you want. In each of this equation, out of these 5 variables, there is 1 missing. In the first one, it is the acceleration. In the second one, there is no displacement coming up. In the third one, there is no final velocity showing up. 4th one, there is no initial velocity showing up. And in the last one, there is no, what's not showing up, delta t. So that's going to be your guide, right? Which equation to use? It's often overwhelming. 5 variables, typically 5 variables are not easy to deal with. Remember, the best we can do is a weather, right? Weather is not a very good, we cannot predict weather very easily. And a weather model has about 17 parameters, 17 variables. That's hard. Even 5 is very hard. Typically 3 is the easiest. 2 given, find the 3rd one, that's easier. 5 is a little hard even for those who can think sharply. But with training, we can, at least in a certain set of problems, we can deal with it. So what's our strategy? In the last 3 minutes, next time we will come back and work on the problems. So what is the strategy is going to be? So 3-step strategy. So I'll squeeze it here. Strategy is, in any given problem, first identify or recognize, identify 3 given quantities. Like out of this 5, 3 is always given, 3 given quantities, let me call it. If you're not able to find them, either the question is wrong, or most often what happens when you're working on homework problems is that you're missing something, right? But the question could also be wrong. Sometimes the information is also there in the words. Something starts from rest, that means initial velocity is 0. something is falling under gravity, that means acceleration is supposed to be known. So those kind of language also has some numbers in it. So it's not necessarily given to you explicitly. So you have to identify 3 quantities in the problem. So out of 5, 3 is already given to you. So that's what 2 remaining, right? Out of the 2, first recognize what is unknown, right? Unknown is what is being asked for. That's your goal. Right? You're looking for a quantity. It will be asked, what is the final velocity when when you throw a stone up in the air, and when it comes back, what's the final velocity? That's your unknown, right? You realize that, oh, that's the final velocity we are looking for. So now we have 3 plus 1, 4 variables gone. That is 1 remaining, and that's not even there in the question. But that's what we want to recognize, or we want to identify. That will be called the missing variable. Missing variable is not being discussed in the problem at all. And missing, ing, right? So that's a missing variable. Why do we need that? That will help us. So look for the missing variable, and that identify the equation, right? So equation to use. If you're good with manipulating equations, you don't have to do this strategy. You recognize, find out any 2 equations, you can do it in 3 steps and you will always get it. But if you use this strategy, you just have to use 1 equation. So start with the problem, identify 3, and you immediately get it. If you want, I can do 1 simple problem in the last 1 minute I have. So let's say that is an initial velocity given to us. So that's 0. The final could be 2 meters per second. And I could be, let's say the time evolved was 3 seconds. And the question could be, what is acceleration? Right. So that's the problem. Immediately I realize, oh, there are 3 problems, 3 quantities given, 4th one is asked, 5th one, what is not given, delta x. Right? This is the missing variable. This is what is asked for. So delta x, I look for this equation, or delta x means this v final is equal to v initial minus delta t. So that's v final is equal to v initial plus a naught delta t. Put in the numbers 2.0. Let me ignore the units for a moment. So that's 0 plus a naught is what I'm looking for. Delta t is 3. And I immediately get a naught is equal to 2.0 divided by 3.0. So that's 0.67 seconds, right? It's a very quick analysis, but we will do more problems next time. Let me not go too far beyond the time limit. Thank you, and we will do more problems next time. Thank you.
Thank you.
Yes.
Just checking to be safe. We're not going to need to be able to do all those equation conversions that you showed us today in homeworks or quizzes, right?
No, you won't need all of them. See, in your homework, you can actually use these 5 equations.
Okay.
Okay, if you want, you can use it. They're always handy. But in your homework, you need only these 5 equations.
All right.
I was motivating these 5 equations. Instead of blindly giving this to you, I was telling you that this is how it comes about. But in principle, in your homework, you don't have to. You just start from here.
Okay. Thank you.
Okay, good.
Have a good night.
Okay, thank you. Good night to you. I'll stay for a few more. Okay, we are down to 4 participants. Let me stop.